Okay, Martin, nod if you can hear us.
Yeah, I can understand you. Can you hear me too?
No.
No?
Oh, we can hear you.
Yeah, I can hear you too.
Okay, excellent. So if you want to share your screen, we're ready for you to go.
Yeah. Can you see my screen?
Yes. I just try stopping this one.
Pun?
Yeah. Yep, we can see your screen and we can hear you.
Excellent. Okay. Should I just start or?
Okay, yeah, so for those that haven't met Martin, he's working at the University of Rostock with Dagmar, and they do lots of cool stuff looking at version control, model histories, and also a lot of work with CellML. And so today Martin's going to talk to us about M2Cat, which is a new name that I haven't heard before. Okay, all yours, Martin.
Okay. Thanks for your nice introduction, David. It's a pleasure for me to again open the CellML workshop. I think it's the third time in a row, and therefore I guess most of you already know me. Yeah, as David said, my name is Martin Charm, and I'm doing my PhD at the University of Rostock. Today I'm going to present M2Cat. M2Cat is a workflow that we've developed in Rostock which helps extracting reproducible simulation studies from model repositories using the Combine Archive toolkit. First of all, let's have a look at the status quo. We already have databases which host tons of model-related data. You all know PMR2, which is probably one of the most interesting. But there are others such as Biomol's database or PubMed, of course. These databases store various kinds of information which is necessary to reproduce a study. There are, of course, models in different formats, such as SBML or CellML, but also simulation descriptions, for example, in ZML, and scientific documentations, such as a journal article and so on. But I wouldn't be there without a gap. And yes, all the data is stored somewhere, but it's actually very hard to find all these documents that are necessary to reproduce a simulation study. A model, for example, might be decomposed into multiple documents, and you need to find all these, and you need to understand the relationship between them. The ZML file might also be stored on a different server and so on. And even if you manage to collect all of these files, it's still challenging to understand how to use them. Yeah, but I probably don't need to tell you that. You of course all know that reproducibility is a challenge. I'm sure you are all familiar with the graphic on the left-hand side. It visualizes the success of Bayer, which is a very big company, with reproducing published studies. They had to cancel almost two-thirds of their studies, of their projects, because they were not able to produce what was published in the literature. Yeah, but you guys are already aware of the issue, and you have a whole slot tomorrow that is called Reproducibility and e-publishing, so you will discuss that later on. The Combine initiative also thought about this problem and developed a Combine archive format. That is a container format to store all the data relevant for a simulation study, together with essential metadata. So you know what to do with the files and who to talk to in case of trouble. And not only the Rostock team was involved in the development, but you guys from New Zealand also contributed to that effort. But I won't go much into detail because David will tell you more about that this afternoon. Yeah, okay. So what did we do exactly? We developed a workflow that is called M2CAT. And M2CAT is about to close the gap between model repositories and the combined archive. It allows you to search for simulation studies in our database and shows the results on a web page and is able to export the studies bundled in combined archives. In the following, I will describe the 3 steps in detail, which are searching for simulation studies in Masimos, retrieving relevant results, and exporting the studies as combined archives using the Combined Archive Toolkit. Yeah, as I said earlier, our goal is to find all files that are necessary to reproduce a simulation study. To search for these studies, we use the Masimos database, which has been developed in our group. Masimos can be used to store models and related data as a huge graph. Here, for example, you can see how we represent a CellML model in our database. This is an SPML model, and this is the representation of a simulation description. But we also store ontologies, such as the SBO. That allows us to link between models and simulation descriptions, for example. But we can also link from models to publications or translate annotation into links to ontologies. Yeah, that structure allows for sophisticated search algorithms. If we, for example, want to search for models from Tyson that contain CDC2, we can ask the person and the annotation index, which select nodes in the model. And the models that match the search result are ranked using a sophisticated algorithm which was developed by Ron Henkel in 2010. M2CAT then use the ranked hits to display them in a list on our website. Additionally, we tell you what kind of resources we found. Here, for example, you see the search result for Tyson 1991. We found a model file, which is apparently in CellML format, but we also found a simulation description to simulate this model. And the database tells us even more information. For example, here it says that the model stems from an exposure in the CellML model repository, where we can probably find even more information on that study. Yeah, and M2CAT then allows us to download the study as a combined archive or to explore the archive in our web interface of the Combined Archive Toolkit. The support for combined archives in M2CAT was implemented using the Combined Archive Toolkit. The toolkit was developed by the 6 of us from our group in Rostock. It consists of a library to create, read, and modify combined archives. This library can be integrated in other software projects. And yeah, so we built on top of that a graphical user interface and a web interface. On the web interface, you can quickly explore combined archives from other websites. You can modify them and create archives and upload your own files. And you can, of course, share the archives and your workspaces with others to, for example, develop simulation studies collaboratively. Yeah, and this is what you see if you open the archive for the previous search result in our Combined Archive web interface. So this is the result for the Tyson 91 study. There's this CellML file and the simulation description that we found in Masimos, next to plenty of other files that we discovered in PMR2. So there's, for example, this PNG image or an SVG file. Every file has some metadata attached to it, as you can see on the right-hand side. So here it's displayed for the model file. And you can see, so here is, for example, the format stored in as an identifiers.org URL for the CellML format. The combined archive web interface tells you when it was created and when it was modified. So you see it was developed between 2006 and 2010. And of course it tells you who contributed to it and who modified it. Yeah, and no matter if you downloaded the archive from the M2CAT website directly or from the combined archive web interface, the archive can be used in other software tools to reproduce the simulation studies, because that's the idea of it. Given all the files in the archive and the metadata that is stored along with it, a simulation tool will be able to understand and run the encoded simulation. Yeah, let me summarize what I presented. I introduced a workflow to extract simulation studies from model repositories in a combined archive format. I exemplified this workflow on our web tool M2CAT, which searches in Masimos and uses the combined archive toolkit to generate combined archives. You can easily try this out on your own on our website. Yeah, but keep in mind that it's currently just a showcase and we are working on that tool. Yeah, however, the single components can be easily integrated in other software tools, and our code is available from our website. Yeah, thanks a lot for your attention. I'd like to thank the SAMS group, especially Martin Peters, who developed most of the stuff I presented now and created all these nice looking figures. And yeah, I'd like to thank the Combine initiative and all our collaborators. And now I'm happy to answer your questions.
Cool, thank you, Martin. Any questions for Martin? And maybe just if you do up to the microphone. No? How do you get the, I probably should know this, but how do you get that version history into the, you're pulling that into Masimo?
We get the version history from the JIT repositories on PMR2. So we traverse the log more or less.
And that's pulled into the Masimo database? Or is that pulling that in?
No, Masimos just knows the most recent version of a file, and the M2CAT tool looks into PMR2 to find out when it was modified and who contributed to that file. So as soon as you search in M2CAT, we clone this repository from PMR2 and have a look into that.
Okay, cool, thanks. Any other questions? No, I guess you explained it all too well.
Cool.
Thanks for that, Martin. It worked well.
Thank you.
So we should move on to the next speaker, which is that guy. And I've lost everything. There we go. Okay, so we'll just unplug that.
Let's grab this.
So this is the camera that's going out to the world, and possibly a microphone that might or might not work. But if you want to do anything dodgy, don't do it in front of us.
I think it's up here anymore, do I?
You share your screen.
Ah. Oh. We're not sharing at the moment.
No, I still have it.
So, screen 2. Is that correct?
You may begin. Sorry.
Okay, so for those of you who don't know me, I'm Hugh Sorby, and I'm a software developer at the ABI, and I spend the majority of my time working on map clients and related projects. And I have lost my notes. Okay. So, oh, good. What is it? Aside from being poorly named, it's a cross-platform, cross-Python Qt-based desktop application. It's a framework for managing workflows or best practices for repetitive tasks. It's looking at enabling researchers to share their research with other people, and it's trying to get our outputs like our segmented data from MRI images, a simulation output from CellML experiments, or sharing our meshes that we create, in particular those ones that we're using from OpenSeam Iron and OpenSeam Sync. It's a plugin-based application that enables users to make use of and share their software through a simple plugin interface. It's named after really the CAP client, the Cardiac Atlas project client, with its initial focus being on the musculoskeletal system, hence the name. However, it's not just for the musculoskeletal system. It's not all it is designed for. So where is it? Well, there's some documentation available on Read the Docs. There's some user documentation up there and some developer documentation. Can't really see it here. The screen's not long enough. So the user documentation is the map client manual. It's just really the instructions on how to install and get set up. There's a quick tour of the application so you can get to understand it easily. There's some instructions on how you go about constructing a workflow. It's drag and drop based. We just grab our steps and connect up ports to transfer the data-driven aspect of it. There's some more documentation on some of the features as well, about the things like the wizard tool, the annotation, and the PMR tool that it uses. And it has some sections on how to write plugins for the application, which includes some tutorials to help people understand what that actually involves. So there's also developer documentation available up there. It's very much more developer oriented for the software, the application framework itself. It's a lot of it is about getting set up with Git and getting map client software set up for development. and how to contribute back your code to the project. So in my view, a good project must also have good documentation, so there's a bit of effort gone in to try and make it accurate and first port of call for people trying to use the project. So the source code, it's an open source project, naturally. It's available on GitHub, written in Python, as I said before, and the application itself tries to follow a model view architecture. We have the model split away from the view, so we theoretically could put any view on top of our model, but I don't think anyone else is going to really go down that route. So currently we're working towards the release 1.0. We're trying to get some features in at the moment. It is expected really that most people will develop their own code into plugins and not the framework itself, but rather any issues or bugs that they come across, they will raise it with developers, myself, and some others who come and go, and let us fix those problems for you. So why is it around? I guess one of the big things is similar to what Martin was saying, but one of the things we're also trying to do here is capture in the first place the software that students are creating. We're trying to sort of resolve a situation where a student moves on from their studies, maybe leaves, in particular, say the ABI, and the computer that they're working on is left behind. They don't care for it anymore. At some point, eventually, the IT department will come and claim their computer and wipe the hard drive, and quite often we will lose any software that was written on there, and that becomes a problem when we want to reproduce some work that this software produced. Maybe it was based on some paper plot or a CellML experiment that someone wants to reproduce. So whether this is through failure of procedure, someone's not handing over their software properly, or people just don't care, we don't want to lose this. It's quite valuable information and data that we'd like to keep a hold of. As to the reproducibility, we obviously want people to be able to reproduce our work. There's a big issue everyone's talking about it. In the map client context, we're trying to reproduce our own software efforts, so that maybe our supervisors can get up to date easily. They can check up on our current status of our software quite easily without having to go to too much effort. And other people outside of our research interests. It's often seems to me a difficult task as to where you draw the line for reproducibility. Do I just give you the software that I created and you go off and fill in the rest? Or do I box the whole world that I produced my output from and give you that? Neither of those two extremes are going to work. So we are doing a step-by-step and just trying to expand our little universe and get deeper into this problem. So at the moment we are looking at getting people to store their software that they create in a sensible repository. Some sort of distributed version control system would be ideal, and then also their dependencies that they're relying on. So we're trying to help people define what dependencies their software is currently dependent on. So it's just a step further than just the software itself, but it may not be enough of a picture to reproduce everything all the time. We also want, where's my button? We also want people to follow best practice. By that, I am really wanting people who don't really understand software development practices mean, obviously have no interest in them quite often either, have no real desire to learn them. We want to try and get those people, and one of the ways that we're looking at doing that is removing as many barriers as possible to some of these ideas like version control and software management. So the idea here is we're going to try and teach these people by stealth. We're not going to be up front and tell them that we're going to teach them about Git, DVCS, and in our case Git and Mercurial. And we're not going to teach them about software management, how to look after their dependencies and find stuff. We're going to try and do this on the sly without them really thinking that they've actually been doing something useful. We also want to make use of other software projects, making use of some of the other work that goes on around the place, especially those projects that are developed within the ABI. We are trying to make use of a number of the projects, and in many cases we're just trying to simplify these complex codes so that other people who aren't familiar with that area can make use of these tools as well without having to know the details at too great a level. Oh, I'm behind. I'm one behind you already. Here we go. Funny. So these are some of the software projects that we're currently trying to make use of. There's OpenSeamless Iron there, which is the computation library developed at the ABI. It's, I think, in my mind, too complex for most people just to pick up and use. Sometimes we want people to make use of the software and not know how to use it, or even in the case that not even know that they are using it is what we're trying to get in some cases. So this happens for us in particular in musculoskeletal modeling problems. So quite often we have people interested in the dynamics of the knee. They're not so interested in the stresses and strains of the fibers in the rectus femoris, although it does actually have an effect in how they create their models for that dynamic movement in the knee. So with more knowledge about of the stresses and strains in the fiber, they can get a better modeling output from when they're doing the modeling of the knee. So we're trying to use this information while not exposing them to the full beauty of OpenSeamless Iron. We're also, whilst we're working towards using OpenSeamless Iron, we'd like to. It's not currently available on the Windows platform. It's taken a brief hiatus from Windows support, trying to get that back so we can make it more accessible for all the platforms that MapClient currently supports. And we're also looking at making OpenSeamless Iron available through web services, so we can access more powerful computers by running our task simulations on a more powerful computer, not just our local desktop. So OpenSeamless Sync is the visualization software that we use that the MapClient is quite tightly using at the moment. Obviously, the models that come in and out of OpenSeamless Iron. Hopefully, with the improved interoperability between those two, we'll get some better user experiences, and the MapClient can have a lot simpler code. It'll be handy for me. So we also talk to the PMR quite a lot. We make a good use of the Physio Model repository. I call it PMR. So this is where MapClient looks to store and retrieve not only the workflow information but the inputs and outputs that a workflow may produce. And it uses some of the features of PMR, such as its searching functionality. It actually has various types of searching that we can take advantage of. There's plain text, we have semantic annotation-based searching that we can use, and we also have some workflow-specific stuff that is a slight hack to make my life a little bit easier, I guess. Trying to squeeze that back into the semantic workflow would be nice. Searching would be nice. So there's lots of other web services that we use in PMR. A lot of it to do with managing our workspaces, our repositories, annotating our data so we can make use of the annotated search, and allowing other people to view our data that we have stored up there. So we're also trying to use CellML just to be friendly to everyone. I see CellML as strictly an exchange format. I don't want to interact with it at all. I want to be able to edit a graphical interpretation of my model and deal with that. I don't want to be looking at XML form of CellML as I currently do if I'm having to muck around with the model. So trying to develop some tools using libraries that are available so we can manage our models in a much more intuitive fashion. And OpenSim here is one of the last ones I'll quickly talk about. This is for developing models of the musculoskeletal structures and creating dynamic simulations of movement, like the knee joint, hip does the full body. But it uses simple straight lines and points to represent its bones and its muscles. So it doesn't really have the in-depth information that we get from our OpenSim style models of full human meshes that we can simulate. So we want to enhance the OpenSim modeling with our better models from OpenSim, and then we want to use those computed values from our OpenSim models and feed them in as boundary conditions to our OpenSim model to hopefully create better outcomes for our clinical patients. So what is MapClient currently being used for? One of the first use case, this main case of MapClient being used was to create this workflow here, which was to automatically segment major bones in the leg. This work was also extended to include the hip bone. So this makes use of a PCA model somewhere in here. It brings in this PCA model of the hip, and it takes some input information, some PCA models, some traditional markers, and some image data, and it will automatically segment the data, and it will take anthropomorphic measurements from the model and put it into a population database. So the idea is that we have a lot of information on the population and how the femur grows for different sizes, so we can estimate some properties for medical devices like our implants that are quite key to how we live our life today. So what are some of the next steps we want to do is make this database that we have searchable and available through PMR. So we need to be able to annotate this data and obviously annotate it with RDS style statements so we can get some more meaningful searches done. Would be great. Another use that we're currently working with is the FAI, the Femoral Acetabular Mucosa study, not the FAI. Got on somebody. So this is a study that's being run over 3 centres, Melbourne, Sydney and Auckland, and they're collecting large volumes of data. They're doing per patient scans, MRI, and they're getting fiducial markers, and I don't know all of what they're getting, but it's in the gigabytes of data per patient, and you're looking at doing hundreds of these patients. And what they want to do is, with new researchers coming in over the course of the study, they want to have an interface that is easy to learn and foolproof, not idiot-proof. That's probably going to be too difficult. But they want to create these workflows where the researchers can easily store the data onto a server, make it accessible to other researchers in the study, run simulations on that data, and be able to reproduce that same simulation results in different locations, and be able to share the actual developed software that they use to create those simulations. So they're currently trying to use the MapClient to meet those needs. So that is me, I think I've talked long enough about that. And a lot of thanks go to the Auckland Bioengineering Institute, of course, and the FDA who supported a lot of this work currently to date. Does anybody have any questions?
Do you have any thoughts about how you deal with data management? Like how you integrate data management to your code? That still seems very difficult to me.
Yes, well, I mean, what we're trying to do is have tools that will annotate our data and store that annotation on here and get it indexed. We're trying to work on ways we can store that data somewhere. We're not too fast. We're trying to come up with best practice for the data storage and we annotate it and get the annotation on UMR, and then UMR will then put it in the database so we can then write the scope and do it. So that's what we're thinking. That's what we're currently working towards. We're currently is make these best practice data service so people can understand how what a good way of going about this is and make it really easy for them. Decomplicate some of these rather complicated situations.
Is there any visualization research issues on this platform related to the visualization research issues?
Visualization issues. No, we use OpenStreetMap, which is a visualization library. We use OpenGL, so I don't have to know much about that. But what we use that is we just create an OpenGL context to compute, which is quite easy. It's OpenGL widget. And we can bring the OpenStreetMap into that. So we can do visualization purposes through this. So I don't know to do other visualizations. That kind of stuff is just a framework around these steps. What are the issues? That one is stable on the label that's designing who it doesn't line itself on the best kind of work on that. And hopefully but we also don't do this research Yes, I think it should be. I hope I certainly probably thinking the combine and we're looking to standardise a lot of that kind of stuff around things like this combine archive. As long as they have web services that we can use, we should be able to deal with it well.
Yeah, hi. I'm Deb Rowe. There's not quite a number to talk about. I've been doing agent-based modeling in various contexts. What I'm going to talk about is linking CellML into agent-based models, or my agent-based models. So I'm not going to be talking about the models themselves. So this is the motivation. Previously, I haven't had any need to use CellML in the kinds of things I've been doing. But this has changed a bit now since I'm helping Nazanin Ibrahimi, who's sitting out here in the corner, if you don't know, who's working on his mouse heart development project. So Nazanin has been trying to develop CellML models that will account for the way these heart cells develop and grow. And the idea is to connect this into a model that enables that to reproduce or try to reproduce the overall behavior of one stage of the mouse heart development, which is the bending of the mouse heart tube. So the starting point for this was the library that David developed called CSIM. And CSIM really, David did all the hard work, basically. All I've done really is create an interface into this library of David's. And so, you know, the engine of my CellML models are all written in Fortran. I needed a library that I could link to from Fortran code. And so that's the library there. I'm calling it ADM CSIM MP, where the MP is for multiprocessor. These are the kinds of subroutines or functions, methods that are made available first to set up a simulator and then to be able to free it, to set the state for a given simulator. So KSIM is the index of a particular simulator. To set the state and to get the state, which is a vector, or to set an individual state value, that is a value for one particular of the variables in the CellML model, and get the ID, single-step processing, single-step solving, or multi-step solving from a start time to an end time, and resetting, which turns out to be quite important. So I've just got a little bit of code here, which you don't necessarily, won't necessarily be of much interest, but the point is that the agent-based approach, there can be hundreds or thousands or even tens of thousands of individual agents, cells, in this case, and each of them wants to have its own instance of a CellML model, because it's got its own state, it's got its own evolving state, and they all are evolving in different ways depending on the signals they're receiving. But it's not practical, of course, to have this vast number of simulator objects being created. I mean, it would, apart from anything else, there'd be memory problems, and also you can't execute them all at the same time anyway. But so the approach I've taken is to specify a number of simulators that will be created, and then these simulators are shared by the cells, and the only thing you have to worry about is making sure that you're not trying to use the same simulator by two different cells at the same time. So each cell, as it's generated, as it's created in the model, either initially or through cell division, is allocated sequentially a simulator index, KSIM. And then when the cell is updated, an individual cell is updated, what happens is the state, or first of all, there's a signal which is achieved from somewhere, as was shown here in this case, for this simple model, it was state variable with index 17. So that's set up in the CellML state vector. Then the KSIM is the solver, the simulator for that cell. I reset that integrator, and then set the state in the simulator to the state vector of that cell, K cell. As a multi-step solver is then called over that time step dt, and when it's finished, retrieve the state and store it back into the cell's state vector. So it's very simple. And using parallelization, it's a shared memory parallelization, which means on a machine like this, it's using up to 8 processors, but eventually running on the cluster we could use more. And so I set up a group of cells to solve in each call to the parallelization loop. So this is done so there's no more than this max simulators number, no more than 32 is the case I've shown simulators, and then that's just a parallelized loop. So they'll be distributed out amongst the processors until they're all done, and then we go back to the beginning again and set up the next set of cells to solve for, and so on. If there's an error, then we go out. So that's very straightforward. There's nothing much to that. And what I'll do now is I'll just give you a quick demo of a little demonstration model that I set up as a proof of concept. All I did was I took an existing model and I made some modifications to it to run this Nazarine's CellML models.
Yes. Is there any very distinct difference between OpenMP and MPI, just the normal MPI library?
OpenMP is a shared memory, a parallel system. Yes, it's quite a distinct difference between that and MPI, in which you have in the OpenMP you have one master program, right, with threads which are spawned from it for the different instances, for the different parallel instances. In MPI you have a completely different instance of the program running on every processor. So MPI can handle much larger scale parallelization than shared memory. Shared memory typically are limited, I think the current limit's probably about 32 or something of that order, right? That's how many processors there are sharing memory on a machine, on a cluster, not on a PC. Whereas on MPI you can have thousands. So this, what I'm running here, has got a lot of stuff in it that's not related at all to what we're talking about. So you have to ignore a few things on here. Just focus on the left-hand side of the screen. So I had some variables which are related to the scale of the lattice. This is a lattice-based agent-based model, but there's nothing about using the CellML code which restricts it to the lattice. This is just the way that this model has been set up. So I can, here for example, there's a number of CPUs I'm going to be using for the simulation. So just for this case, I'm going to select one of these models that Nazarine developed. This is the Wnt cyclin model for cell proliferation. And so there's a single signal driving this model. It's really just for demonstration purposes. So I've selected the CellML model and I load it, and now I can look at it. So in this case, the model has just a single component called whole cell, and these are the variables. Some of these are fixed parameters. Some of them are variables that will change as the cell executes. So you can change values in here if that's desired, and then execute the model. So there's a bit of a delay here. What's happening is it's generating this 32 different instances of the CellML simulator in David's library, and now it's running. And so this is the usual way I see what's going on in the model. There's a BTK display. And in this case, the color of the cell indicates which stage of the cell cycle it's in, G0, G1, S, G2, and M. So, and for demonstration purposes, a very artificial case where we have the signal, which is driving this, is at a maximum at the right hand of the blob, and it's decaying in an exponential way at a specified rate off to the left. That's why you see these cells on the left now have stopped dividing, because the signal is now too low at this point. So that's why it's all stuck in G0. These are the parameters here. So there's a cell cycle time, which is the average time, if there's a sufficient signal, the time that it takes for the cell to go through the cycle, the amplitude of this driving signal, the decay coefficient, and another cycling coefficient parameter. So that's it. As I say, this is just a very simple demonstration of this linking of David's library into, so that being able to have multiple instances of the cell going at once. Just, that's it. Thank you.
When a cell proliferates or divides, when you start off with 32 cells and you created T7 implementation of...
Let's start with 32 cells, start with 32 solvers. The 32 instances of the CellML simulator, but they're shared. So I can have any number of cells that I start with, and they're solved for in groups of 32. They're updated. Their state is updated 32 at a time. So that there's a reuse of that cell simulator, because each time it's reset, the state of the current cell is loaded into it, and it's run through it.
So there's no limitation as you...
No, that's not. It can go itself.
How much of what you've done specified your agent-based modeling simulator? How generalizable would be your approach to coupling CellML simulator into if I had another agent-based model?
No, I think it's very general. It's just a library with that set of methods exposed. Yeah, so it's completely general. Sure, you're welcome.
Is there any study related to like the convergence rates of the state? I mean, I don't know if it's just a general multi-channel convergence of the states. Is there any study related to the state, like convergence rates of the states of a model? Like, I think this demonstration seems like trying to show that some instance of agent runs toward G0 state.
No, it's nothing like that. All I'm doing is showing a linkage of CellML to a system which has multiple CellML states within it. That's all. In this case, the signal just drives cells continuously to go through the cell cycle. So they're constantly cycling through G0 to G1 to S to G2 to M, and the timing of that is influenced by the strength of the signal that the cell is receiving. And the strength is, in this case, just a number that varies from this side down, exponentially decaying across in the negative x direction.
So you mean that there's some organic cycles of the changing of these states, right? Like organic cycle? I mean, what am I saying? Will that converge to become states from the macro chain?
No, there's nothing to do with, there's nothing probabilistic in it. There's no. The states are purely deterministic. This transition from one state to the next is purely deterministic. Nazanin can tell you about that if you're interested. Sure.
Have you implemented contact inhibition, like cells? And when the cells grow, when they hit the surface, they usually stop growing?
This is just a toy model. As I say, it's got nothing to do. This is meaningless. This model, except to demonstrate the linkage of CellML.
But that's something that should be implemented in the model itself.
Which model?
Any CellML model.
Of what? I mean,
any cell type that grows and
Yeah, I mean, exactly what we do with this is another question altogether. What we use this ability to link CellML, and this is, I'm not talking about that today. As I say, I have several different models using, and for different purposes, right? T-cell activation model for the growth of tumor spheroids. They each have different requirements. But that's not my topic.
Wonder if you looked at kind of the memory use for setting up an unresolved breach agent versus the sort of speed of not having to switch it in and out.
I haven't done any performance testing, if that's what you mean. It'd be simple matter to do it. Very simple.
Yeah, we've taken the same approach for sharing a solver, so the other thing is that it's the state variables in the admin system to share a solver. And we always thought we'd never got to use CBOD, which keeps a bit more information out of the whole time. Then we tried getting it scheduled to meetings and that's just CBOD and separate instance.
Right. That's just an empirical matter as to what setup time is, what the time step size is, what time step size you need to use. I mean, in this case, the actual the time between these steps is quite long.
Yeah, I guess the benefit, if it is an adaptive time set, it can kind of keep that information. It's got a solve on each engine between steps.
Yes, but I mean, if this time step that's being used in the solver is short compared with the overall length that you're solving over, it really doesn't make any difference because it's a very small part. Starting again or starting with the information that you had from the end of the last big time step. Because this is an adaptive solver, right?
Mm-hmm. So this is using CBOD.
It is using. So it's a question of how finely you want to be able to look at the development process. And if it requires a very short time step in between the course to the solver, then this could become expensive to do it like this.
But you are still resetting the CBOD software. Yeah, so that particular step is very time-consuming using CBOD. So I will set up the software once for all solution. I think you could actually get quite a bit of speed up by having this kind of take. I mean, one CBOD sort of prevention.
Well, it's easily tested. Just by changing this number, this parameter, the maximum process, making that a large number, see how fast it runs. Make a small number, see how fast it runs. And it's
resetting the CBOD software.
Yeah, you can get away with certain things like changing parameters or state variables. You have to be a bit careful. If you change it too much, CBOD thinks internally something's got a bit mad and needs to reset itself anyway. We discovered you can kind of do a bit of everything.
As always, there's a balance between memory and process time. Right? So which one's constraining, depending on the problem.
Okay, so thanks to all the speakers this morning, and Martin and Nina are still online. So we're pretty much exactly half an hour late, so we'll come back at past 11 for the next session, and morning teas are coming up now.